My name is Cristian Antonio and I will present at today's webinar Seismic Design of a Reinforced Concrete Structure. We'll talk a little bit about materials, how you define properties, how you can input the geometry in an efficient manner. We'll talk about boundary conditions, surface spring, stiffness reduction, how you can group elements, about domains and subdomains. Then we will apply the loads, the static loads, dead loads, live loads, the dynamic loads. We will use the response spectrum analysis for the design, and how you can use the load combinations. Then we'll perform the modal analysis, and we'll look on the results, and we'll design a concrete beam, concrete column, concrete slab, and walls. So when we start the model, I already have defined a template for this, which includes the section properties and the material properties. So when I start the model, I already have defined all the materials and some sections. I also define some load combinations. So the seismic load combinations, fundamental load combination with snow as a variable predominant load, and with a live load. We have some load combinations amplified for the foundation design. So I prefer to use a template because it's easier, you save a lot of time and you don't have to define those again. And now here in order to input the geometry, I prefer using some CAD file, and you draw the 3D axis of the elements, and then you just import them in Midas. And here are the layers from the AutoCAD, and they already have defined some sections. FB, for instance, is the foundation beam, and you just need to correlate this with the section from Midas. Okay, and then apply, and we have here the foundations imported. Then we can go to the other elements. This is a column 30 by 80. Okay, and we'll go with all the sections. I think I imported this twice. Okay. When you assign the sections, which are already defined by me here, you can see with blue those are not assigned yet. So in case you forgot which section you imported already, you can see them here. I define some layers which are named construction. I use those layers in order to import the openings in the slabs or to define the concrete walls. And I'm using some fictitious materials, and in order to be easy to select them later and delete them. So you can see here an opening in the slab. And now we have only the steel materials. I define also some rigid link, which is related to some eccentricities between elements. We have also some steel elements. Okay, and this is our structure. You see we imported it very fast. When you define the section, it's for instance we have those two sections. The difference is the insertion point. You can change it from here. And this basically connect the center of the elements with a rigid link through the insertion point. So basically you take into account how the loads are applied. Another very good feature of Midas is that you have the 7 degree of freedom, which is considering the warping effect, and is very useful, for instance, when we have like cantilevers like we have here. And now I think we have the section, the main elements imported. You can very easily rotate them from here. You have change parameters, and from here you can change materials, sections, thicknesses, and also local axis. Okay. Okay. Now Midas, in order to model the walls, you have two options. So you can use auto mesh, and you will mesh the walls and you will have some shell elements. But also there is the option which is called wall, and this is a special type of finite element from Midas which doesn't have to be meshed. Okay, I think this was the only wall in the model. Those are modeled as beam elements because they are not very the ratio between the thickness and the length of the wall is not that big. Okay, now we can start model the slabs. Let's start with the ground floor, and we can use the auto mesh module. We select the nodes, we select the maximum size. Here you have plate elements, and you have thick plate elements and thin. The difference is if you consider the shear force, we'll select thin, and we have some 15 centimeters slabs. We select the nodes and it will divide the slab. Okay. Now let's go to the next one. And those are 13. Now we can go to the next one. Okay, we have two more. And now we have the terrace slab. I define this in a separate section because it's very easy to select them from here after that. You can activate You can add to the window other elements, select, unselect. So it's very easy if you have different sections. Okay, so we managed to import the whole geometry in about 15 minutes. So it's very convenient to draw first the axis in AutoCAD because you usually start from an architectural layout or from a formal plan. So it's very easy to do the model like this. So this is our model. As I show you, we have some fictitious elements here which were used to define some walls or some openings in the slabs, like those one from here, and we just select them and delete those layers. Okay, now it's fine. We have a few adjustments to do. For instance, this element, it's imported as a beam, but in Midas we can import it as a tension only elements. Those are some steel ties for the steel elements. Okay, we'll have to rotate this section also. In order to assign end releases, you can use this one from the boundary menu. And I think that's it. Now we can start input some springs. So we select FB is the foundation beams, which are some inverted T sections which were already defined. The insertion point is on top, and we activate them here. So there are different methods. You can either use some supports to define under the columns if you have some isolated foundations. In this case, we'll use some surface springs. We select the foundations. We can use distributed springs, and we define we mention the width of the foundations, subgrade reaction, which can be compression only. Okay. So those are some vertical springs in order to take into account the flexibility of the soil. And we can define also horizontal springs, but for this case, in a simplified manner, I will just fix some nodes on the lateral direction. Okay. Now we define the boundary conditions. Before starting to add loads, we still have a few things to do. One is to do the panel zone effect. Basically, this take into account that the elements are modeled in the axis, and you have this which overlaps here, and in order to have a realistic deformation between those elements you need to use the panel zone effect, and this automatically will calculate the zone offset and will add some rigid elements here, and with a factor of 1 it will automatically calculate, or you can reduce it for instance to 0.8 or something like this. But first we need to select them. Yes. Yeah, so yeah, no, it was added here. Okay, and then in order to calculate the story stiffness, I define two load cases which are fictitious, and we'll add 1 kilonewton force in the nodes for that load case. So those must be added for each story. And are used in order to calculate the story stiffness center. We can have here select previous, so it's very easy to assign also on the other direction. Okay. Now we can define the stories from here. We have auto generate, and we have the stories already defined, and we can add also the last one which is here. Okay, and we can consider floor diaphragm at those levels. Those are the display options. At the boundary we can check the diaphragm which was added, and it basically connects all those nodes from this story. Okay. Another important aspect, because we are dealing with concrete elements, are the stiffness reduction. And we have, this one is for the beam elements, this is for wall, and this is for plates. So for beam elements we can reduce by element, meaning each element from the model, or we can reduce by section. And I already, basically you select the section and you define for each section some scale factors for area or for inertia or weight, and I already defined those here. For the plates elements you need to select them, and we can select them from here. And assign a stiffness reduction. Okay. And I think the model is ready. We can start applying loads. And in order to be easy to manipulate the results, we can define some groups. So I define, you can define from here, structure new, and you can put the name of the group. And I define here the terrace slab, and here is the current slab. Okay, so this will be okay. Now you can select the elements from here, very easy. I will use those groups in order to assign the loads faster. Now we select all the slab. We can unselect those, and those will be for the terrace slab. On those elements we'll apply also the snow load. Okay, we can save the model, and now we can start applying the loads. So let's start with the terrace slab. We have here the pressure loads, and we have permanent loads. We can apply them globally, minus 3 kilonewtons per square meter. Then we select the current slab and we apply another load. We can move to live loads. And the snow load on the terrace. Okay, so we applied all the gravitational loads. Now we have to apply the spectrum, to define the spectrum, which is from the loads tabs, dynamic loads response spectrum. And you can add the spectrum. You can either import or design one from Eurocode. You just input the parameters and you'll have the response spectrum. Here you have the scale factor in order to take into account the behavior factor. You need to pay attention to the units when you are if you are importing a file. I prefer I have some spreadsheets where I generate automatically the spectrum, which already take into account the behavior factor. So this is the inelastic response spectrum, and you can just paste here from any kind of file, from TXT file or Excel. Okay, so now we are ready to run the model. You can see that it was very easy to build a model in about half an hour, and it's not very complex, but it's not an easy model. So it's for me it's very easy to use this procedure where we are importing a CAD file, but you can also draw elements and axes if it's let's say better, if you are used to do in this way. And now we can go and run the model. We define the eigenanalysis. We have subspace iteration, reads, and also let's have a look on the results. So from the results tab, we can have a look at the vibration modes. So this is the first mode of vibration. We have 0.5 seconds. We can see it is a translation on X direction. The second mode of vibration, we can see it's a translation on Y direction. And the third one, we can see it's a torsional mode with 0.37 seconds. We can check the results also in tabular form at vibration mode shape. We have 50 modes, and we can check the model participation for each mode. We can see the first one it's on X, the second one on Y, and then we have a torsional mode. And here we have the sum. We can add more modes if needed. I took only 50 modes for this analysis. Then we can have a look on displacements. So let's check, for instance, the fundamental load combination with snow as a predominant variable load. So we have about 2 centimeters, 2 centimeters the maximum deflection. And let's look on some seismic load combinations. Okay, you can see the displacements also for each load combination in a tabular form. So for history nodes, you can have the displacement. You can check also the drift. And here you have either you input the coefficient or the response modification coefficient, and you can automatically check the drift for all vertical elements or at the center of the mass. Let's have a look on some bending moments diagrams. So we can see the maximum are at the foundation beams. We can inactivate those to see the columns and the beams. So those are the maximum moments. You can see here on the diagram the difference is between is that the panel zone effect, where we consider the difference between the axes of the elements. And we can very easily check also the pressure, soil pressure for the foundations. Let's look, for instance, for the fundamental load combination. we have about 200 kilopascals, but we can check also for the amplified load combinations. Let's look for the envelope, and we have about 240 in this part. The amplified load combinations we use in order to check the infrastructure. We can have a look also on the steel elements. So we have some steel columns here, and here we have the cantilever beams and the ties. So we have about 15 kilonewtons meter. Those are the stresses. You see we have also the 7 degree of freedom, which corresponds to the warping of the section. And now let's look a little bit on the design code checks. So for the design we have the load combination tab. We have to import the corresponding load combinations to concrete and steel design. So they are already imported here. Okay, and let's have a look on the checks. So first we have to define the rebars. So this is the 30 bar 30 column. We can define the same reinforcement in all the sections, or we can define each bar separately. For this one I will use the same reinforcement everywhere. Let's put in the middle the spacing for the stirrups at 200 millimeters. And I think that's it for this one. Okay, and we defined the reinforcement for the beams. The design codes parameters are input from here. We have the Eurocode 2, and we have the high ductility class, and we have also the check strong columns weak beams. So the parameters are fine, and we can check the beams. Okay, so from here we see for each property the most the worst case for each member, and here at the graphics we have the details for the most severe load combination. We can choose the members in order to see for which elements are failing, and with connect model view we can see exactly where we have problems. So I think there are all the sections from here. Okay, then we can increase the reinforcement for this one. Okay. You can perform the check for all the elements, or you can select the elements which you want to check. I will select only those. And those are the checks which are failing. We have some problems with the shear forces. So we can reduce the spacing or increase the diameter of the stirrups. Let's have a look also on the columns where the procedure is the same. Let's propose a reinforcement like this. And the columns will be checked at the amplified seismic action, considering the strength, the resistance of the beams. That's why here they are asking to check first the beams in order to calculate the bending capacity of the beams. Okay, so we have some problems also here with the rebars for the shear check. We can see here at the graphics the checks. So we have the bending moments. Here we have the normalized axial force and the interaction between the axial force and the bending moment. And here you have also the joint check, which depends also on the reinforcement of the beam. And here at the, if you select a member, you have all the detailed calculations using Eurocode. Now let's have a look also on the color on the walls. So for instance, let's use at the ends bar with diameter of 16 at 10 millimeters. Here we have the cover, the concrete cover, and here we have the boundary element lengths, which are the end of the walls where we have bigger reinforcement. Let's say we have 350 millimeters. So like this, and this is the reinforcement from the middle. Let's put diameter 12 at 150 and like this. Okay. Okay, and this is the check of the wall. So I think I choose the boundary element a little bit too high for the length of the wall, comparing with the length of the wall. Okay, but the shear check and the bending checks are fine here. Now let's design also a slab. Well, for the slab you need to go to define domain, and you can give a name to each slab, and then you have the subdomain. I already defined the terrace slab, and here you can input thickness. I use the thickness from the model, which is 15 centimeters. You define the type of the member, and then you define some basic reinforcement. Then from the design tab we can let's select the slab first. Okay. So from here you can see the reinforcement. So those are the reinforcement for the beams, from the column we check, and for the wall, and those are the reinforcement for the slab. Okay. Let's have a top view. And then from the design tab we have the mesh design, and you can check also shells if you have walls, let's say, or other kind of shell elements. And here we have the slab. We go to flexural design, and let's see for the top rebar. and is the direction 1, which is X direction. So we have bars with diameter 10 at 200 millimeters. This is on top, and on bottom we have 8 millimeters. And here we can check the area per meter, and here we have the resistance ratio. So let's take a look on the top. And here is the utilization coefficient. So we have 1.6 in this part, which is let's say the most loaded slab. At contour we can easily check where we have failing. Yes, so here in those parts we need to add supplementary reinforcement. Let's check also on the bottom. Here we can see those are the most loaded slabs, but they are below 1. And let's have a look on the other direction, on the top. Here we also have some failure. Let's have a look to see where it is. Yeah, so we have here some slight, let's say, and also here we have some failure. So we need to supplement the reinforcement from here. Now let's have a look also on the bottom. On the bottom we don't have problems. And what you can do is you can select the slabs where you have problems and add some supplementary bars beside the basic rebars. But for this case I will just increase the reinforcement everywhere. Let's put 12 millimeters and let's put also 10 on the bottom. Okay, now we can check again for the top. Now seems fine. We still have some slight some failures here near the intersection of the beam, but there are some stress concentrators due to the presence of the columns. And let's look also on the other direction. Here seems to be fine. Maybe here we have some slight some failure here in the slab. So this is how you check shell elements. We can have a look also on the steel. Let's select, for instance, the IP elements, and here at the design is the same as for concrete. You need to go to the design code and select what options apply to you. For instance, national annex, if the girders are laterally braced. And then we have the steel code check. And we can see that the utilization coefficients are fine. This is the detail calculation for steel. And here it's a graphical report with the checks. And you can have also view result ratios. For instance, for this. And you can see the results for all the elements here. So those are all the beams which have this section. So this is what I wanted to present. I focus mainly on the modeling part because you saw it's very easy to build a model in Midas. My approach is to use some CAD files in order to build 3D geometry using lines in different layers, and then the layers from the CAD file must correspond to the section you want to assign to the model. And after that it's a matter of let's say few minutes depending on the model to import the geometry, and then you have only to mesh the slabs and to add the loads. Then I presented briefly the design module where you can input some reinforcement for beams, columns and walls. Then you have the mesh design, which is used for shell elements, and I showed you some example of the terrace slab. But you also have the option for design plus, which is connected to Midas Gen, and you can import the loads and the geometries if you have more complex geometry, for instance some L-shaped elements or some central core walls. So this is what I wanted to present for today. Thank you for